This is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering. So, in this lecture, we'll discuss some problems on full wave rectifier. So, as we all know about the rectifier, and we have studied, we know the mathematical analysis of full wave rectifier, that is center tap full wave rectifier. So, we'll just recall the formula related to the center tap full wave rectifier. Then we'll see the problems on the center tap full wave rectifier. So, first of all, the maximum current flowing through the rectifier circuit, that is center tap full wave rectifier, so is represented with Im, and it is given by Vm divided by Rs plus Rf plus RL. So let us have a look at the center tap full wave rectifier. So here in this we have step down transformer in which the secondary winding is having a tapping at the center. So which makes a secondary winding, which divides the secondary winding into two halves, and two diodes are connected, one to the upper half of the secondary winding and the other one to the lower half of the secondary winding. So anyhow, we'll use a step down transformer in this one also. So here we have a tapping here. So this makes the secondary winding into, or else this divides the secondary winding into two halves. This is the upper half and this is the lower half. And we have connected two diodes here. This is diode D1 and diode D2. And here we have got a load resistor connected in between the cathodes. That means the two cathodes of the diodes are connected together, and the load resistor is connected between the cathodes of the diode and the center tapping. So here this center tapping acts as a ground. That means we can say that the load resistor is connected in between the cathodes and the ground. So here we'll get the same voltage in the two halves of the secondary winding, which is Vm and Vm. Okay, so that means the tapping divides the secondary winding into two halves, which divides the voltage equally but in opposite polarity. So this is the center tap full wave rectifier, and the maximum current let us have a look at the operation. So during the positive half cycle of input voltage, we have, so the point, let us consider this as point A and this as point B. Point A becomes positive and hence the diode D1 is forward biased, and point B is negative during the positive half cycle of input voltage, which makes the diode D2 reverse biased. As the diode D1 is forward biased, so the current will be flowing through the diode D1, which is on, through the load resistor and through the center tap, that is the secondary winding of the transformer. And during the negative half cycle, reverse happens. This point becomes negative, this point becomes negative, and this point becomes positive. So which makes the diode D2 forward biased and diode D1 reverse biased. Now in this case, the current will start from point B, will flow through the diode D2, which is on, and through the load resistor and through the secondary winding of the transformer. So that means in either of the cycles, there will be current flowing through the load resistor, which is very positive. That means which leads to, in both the cases, the current through the load resistor is in same direction, and hence we'll get same current through the load resistor, which is having only positive half cycles, and that is represented here, which leads to a voltage across the load resistor, which also has only positive half cycles of voltage across the load resistor. So this is a brief operation of center tap full wave rectifier. So the maximum current is given by Vm divided by Rs plus Rf plus RL, where Rs is the internal resistance of the secondary winding, Rf is the internal resistance of the diode which is forward biased, and RL is the load resistance. So we should remember that Rs plus Rf will always be very much less than RL, because RS is the internal resistance of secondary winding, which is negligible, and even forward resistance of the diode is also negligible. So next, the average current IDC is given by IDC is equals to 2 Vm by pi into Rs plus Rf plus RL, or else if you consider the condition that is Rs plus Rf is very much less than, or else RL is very much greater than Rs plus Rf, then this equation can be obtained as 2 Vm by pi. That means I can neglect these two when compared to this RL. So in that case, IDC, that is the average current, or else the DC current flowing through the load resistor, is given by 2 Vm by pi into RL. Or else in terms of current, we can also write it as IDC is equals to 2 Im by pi. So next, the DC output voltage is given by VDC, which is given by 2 Vm by pi, where Vm is the maximum voltage across the two halves of the secondary winding. And the RMS voltage across the load is given by, RMS voltage is calculated by taking root mean square value of the waveform which we have got here. So that is given by Vm by root 2. Similarly, the RMS current through the load resistor is given by Im by root 2. Next, as we all know that the efficiency is defined as the ratio of DC power delivered to the load to the AC input power from the transformer secondary, which is given by PDC by PAC. So it is PDC, it is PDC by PAC. And we know that the formula, how to calculate the power. So power is generally represented as V into I, where we can also write it as V square by RL, or else we can also write it as I square into RL. So that is why PDC can be calculated as IDC square into RL, where we already know that IDC is equals to 2 Im by pi, and PAC can be calculated as IRMS square into RL, where IRMS is given by Im by root 2. And similarly, the ripple factor is defined as a ratio of effective value of AC component of voltage or current to the direct value or average value. That is ripple voltage. It is defined as a ratio of RMS value of ripple voltage to the average value. That is, we can also write this as VRMS divided by VDC. So that is RMS value. Effective value of AC component can always be found by RMS value, that is root mean square value. So that is why it is defined as a ratio of ripple voltage to the average value, which is given by VRMS by VDC. So the formula for VRMS by VDC, and we can also have another an alternate formula for ripple factor, which is under root of gamma is given by under root of VRMS square minus VDC square by VDC, and we can also obtain the equation as VRMS by VDC whole square minus 1, where VRMS value, you know, VRMS is Vm by root 2 and VDC value is, we already know, that is 2 Vm by pi. So this is the formula for ripple factor. Now coming to the transformer utilization factor. So we know that transformer utilization factor is defined as the ratio of DC power delivered to the load to the AC rating of the transformer secondary, that is PDC by PAC rated. So here in this case, PAC is equals to VRMS into IRMS. So which is nothing but Vm by root 2 into Im by root 2. So we can find it out like this. Next, the peak inverse voltage of the diode in it is a full wave rectifier. In a full wave rectifier is 2 Vm, because we have two diodes connected to the secondary winding. In either of the case, any one of the diode is on, and hence there will be some current flowing through the load resistor, and which leads to a maximum voltage drop across the load resistor. And also the other diode is reverse biased, due to which the entire voltage of the next half of the secondary winding will be dropped across that reverse bias diode. So if you apply that KVL, that peak inverse voltage, that is a voltage drop across the diode, that is a maximum voltage that a diode can withstand without any damage under reverse bias condition, will be Vm plus Vm. Vm is the voltage drop across the load plus the voltage drop across the diode which is open circuited. So it is 2 into Vm. Next, the form factor, it is defined as a ratio of RMS value to the average value, and it is denoted by F, which is given by VRMS by VDC, or else IRMS by IDC. Now coming to the peak factor, it is also defined as a ratio of peak value to the RMS value. Okay, peak value in this case is Vm. Any case it is Vm, and RMS value will be Vm by root 2. So this one will be 1 by root 2. So here, now coming to the peak to, so we'll be as the rectifier output is having both AC components and DC components, but we require the DC components. So we are using some filters. So basically we use capacitive filter. So now we'll see the formulas for peak to peak ripple voltage. So how the capacitive filter is affecting the ripple voltage if we add a filter to the rectifier. So that means if the rectifier output is given to a filter, how the ripple voltage will be affected. So that is the peak to peak ripple voltage with the capacitive filter. With the capacitive filter is given by EDC by 2FC into RL. EDC by 2FC into RL. EDC, or else we can also write it as VDC. So EDC nothing but DC output voltage. 2. F is nothing but the frequency of the signal, input signal, which is basically 50 Hertz. And C is a capacitance which we are using for the filter. And RL is the load resistance. And we can also write this one as VR peak to peak as VDC divided by 2FC into RL. Or else we also know that VDC divided by RL is nothing but IDC. Just I am replacing that. So that can be written as IDC by 2FC. IDC by 2FC. So like this also we can write. This is the peak to peak voltage of the peak to peak ripple voltage with the help of capacitive filter. And similarly, we can find out the ripple factor. So as we are using the capacitive filter, definitely there will be variation in the ripple factor because we are using the filter to reduce the AC components. So if you reduce the AC components, the ripple factor will automatically change. So the formula for ripple factor with the capacitive filter of a full wave rectifier with capacitive filter, which is given by VRRMS divided by VDC or else EDC. And the formula for that is 1 by 4 root 3 FC into RL. So just remember all these formulas so that we can use all these formulas in solving the problems on rectifiers. So let us see the first problem here. In the center tap circuit shown in figure 2, the diodes are assumed to be ideal. Ideal in the case, the diode forward resistance is considered to be 0. That means the forward resistance of the diode is considered to be 0 because we are saying that the diodes are considered to be ideal. Having 0 internal resistance, find DC output voltage, peak inverse voltage and rectification efficiency. So as he has mentioned, center tap circuit it indicates a full wave rectifier and the circuit is shown in figure here like this. So this is the input voltage given 230 volts, that is the primary the RMS value of the voltage at the primary winding of transformer. It is 230 volts and the turns ratio is given, that is 5:1, that is N1:N2 is given here. So I am writing here V primary RMS value is given by 230 volts and here he has given N1 by N2. N1 by N2, which is a turns ratio, which is given by 5 by 1. And he has given the load resistance. From the figure, we can see that the load resistance is given by 100 ohms. So these are the values given, and he has mentioned that the diodes are considered to be ideal, and hence we can consider that RF is equals to 0, and similarly RS is also equals to 0, because the internal resistance of secondary winding also he didn't mention, means we need to consider it as 0. Now he asked us to find VDC and peak inverse voltage and rectification efficiency. So as we don't know what is the voltage we are getting at the secondary winding, we only know the primary winding RMS voltage and a turns ratio. So now we can find VS RMS, that is at the secondary, that is given by, so we have the formula, that is V1 divided by V2 is equals to N1 divided by N2. That means I can find out voltage at the secondary winding from this formula, that is V2 can be obtained as V1 into N2 divided by N1. So that means VS RMS I want to find. So VS RMS can be obtained as VP RMS, that is the RMS value of voltage in the primary winding, into N2 by N1. So VP RMS is 230 volts into N2 is 1 divided by 5. So 230 by 5, which is nothing but 46 volts, which is nothing but 46 volts. This is the VS RMS. Now I am finding the maximum voltage. Just a second. Maximum voltage at the secondary winding. Maximum voltage at the secondary winding of the transformer is represented with VSM, which is given by VS RMS into root. Okay, so now VSM can be find out as VS RMS value, we have already got it, that is 46 into root 2 value is 1.414. So if you find out the value of this one, you will be getting this as 63. It will be approximately, it is equals to 65 volts. That is the maximum voltage at the secondary. But here we have a center tapping at the transformer secondary. So that means the maximum voltage which we are getting in both the halves of the secondary winding can be obtained by VSM divided by 2, where VSM is 65 divided by 2, that is 32.5. That means the maximum voltage is in the two halves of the either upper half or lower half of the secondary winding is given by 32.5 volts. So we have got the maximum value. Now, as we have got the maximum value, now what we need to do, we have to calculate the DC output voltage. The first bit is DC output voltage, which is represented with VDC, and the formula for VDC in case of a full wave rectifier is 2 Vm by pi, where 2 into Vm value is 32.5 divided by pi is 3.14. If you calculate this, the DC voltage, we will be getting it as 20.7 volts. This is the DC output voltage. Now coming to the second one, peak inverse voltage of the diode, which is given by 2 into Vm. So where we already know the Vm value is 32.5. So the peak inverse voltage of diode in the full wave rectifier will be 65 volts. Okay, so this is PIV. Next, third one, we need to find out rectifier efficiency, that too in terms of percentage. So we already know that efficiency is defined as a ratio of DC power delivered to the load divided by AC power from the transformer secondary winding. And PDC can be calculated as IDC square into RL, and PAC can be calculated as IRMS square into RL. So before finding PDC and PAC, we have to find IDC. So IDC value, before finding the IDC value, I have to calculate IM. So what is IM? IM is equals to VM by RL. Where what is VM here? 32.5, because RS and RF are not given, those are negligible. So that is why RS plus RF are considered to be 0, where RL is 100. So this is 0.325 amperes. This is IM, maximum current. Then IDC can be calculated as 2 IM by pi, where 2 into IM is 0.325 divided by pi is 3.14. So IDC value we will be getting it as 0.207. IDC value is 0.207. And similarly, I have to calculate IRMS value, where IRMS value is, formula for IRMS is IM by root 2. What is IM? IM is 0.325 divided by root 2 is 1.414. So if you calculate this one, IRMS value will be 0.229. Then PDC. PDC value is IDC square into RL. As you know, IDC 0.207 whole square into RL is 100. So the PDC value we will be getting it as, if you evaluate this value, PDC can be 4.28 watts. Power is always measured in terms of watts here. And PAC can be calculated as IRMS square divided IRMS square into RL. IRMS square into RL, where IRMS value is 0.229 whole square into 100. So PAC value will be 5.244 watts. Now the efficiency is PDC divided by PAC into 100. So what is that? 4.28. We have calculated the PDC as 4.28 and PAC is 5.244 into 100. So if you evaluate this value, the efficiency will be approximately equals to 81.6%. So this is how. So already we know that the theoretical value of efficiency of a full wave rectifier is 81.2. So it is approximately equal. So that means that the problem which we have done is correct. So that means whenever you calculate any values related to full wave rectifier, these must match with the theoretical values of full wave rectifier. So this is how we can calculate the output voltage, that is the DC output voltage. Next IDC, IRMS, and from that we can calculate the efficiency, which is given by the ratio of DC power to the AC input power. So that is the first problem. Now the second problem, a full wave rectifier is operated from 50 Hz supply with 120 volts RMS value. It is connected to a load drawing 50 milliamperes and using 100 microfarad filter capacitor. Calculate the DC output voltage and RMS value of ripple voltage. Also calculate the ripple factor. So what he asked us to find the DC output voltage and RMS value of ripple voltage, and also he has asked us to calculate the ripple factor. So first of all, let us note down what are all the parameters given. So he has mentioned the frequency, that is 50 Hz, and he has given the rectified circuit is operated from 50 Hz supply with 120 volts RMS. As you all know that primary always will be getting 230 volts. So that means this indicates the voltage at the RMS voltage at the secondary winding. So we can write it as Vs RMS, which is equals to 120 volts. And what is the other values given? Capacitance value it is given, that is 100 microfarad. And here it is connected to a load drawing 50 milliamperes current. So it is this current is considered to be DC, because always from the load we will be calculating or else measuring the DC output. So IDC is given, that is 50 milliamperes. And now he asked us to find DC output voltage. In order to find DC output voltage, okay, so first of all, let us find out the Vs maximum, that is the maximum voltage at the secondary winding. Maximum, we know the RMS value. I want to find out maximum voltage at secondary winding of the transformer. At secondary winding. How can we write it? How can we get it? That is Vs RMS into root 2. That is VSM is equals to 120 into root 2 is 1.414. If you find out this value, you will be getting it as 169.7056. This is the maximum voltage at the secondary winding. So here, now, if you look at the secondary, the center tap transformer, that is a full wave rectifier. So we always will be getting the output voltage, that is the DC output voltage, okay, which is equals to VSS. So here he didn't mention the load resistance. If he has given a load resistance, we would have get the DC output voltage directly, but he has not mentioned any output load resistance. So that is why we have another formula for calculating the DC voltage, that is maximum voltage at the secondary minus as it is connected to a capacitive filter. So we have to, whatever the voltage drop across the capacitor, we need to subtract from the maximum voltage. Then we will be getting the DC voltage across the load resistor. And the voltage dropped across the capacitive filter can be calculated by IDC by 4 into FC. So this formula we have already seen. So in this, this is nothing but what? Voltage drop across the capacitor. Voltage drop across the capacitor. So if you subtract the voltage drop across the capacitor, so that means some voltage will be dropped across the capacitor and the rest will be delivered to the load resistor. So that is why the DC output voltage across the load resistor can be calculated by this formula. So as you already know that V maximum, that is a V maximum voltage at the secondary winding is given by 169.7056 minus IDC is given, that is 50 into 10 to the power of minus 3, because IDC value is 50 milliamperes, and 4 into F is 50, and C is given, C is 100 microfarad, 100 into 10 to the power of minus 6. So if you calculate this value, then we will be getting that VDC value as 167.2056 volts. This is VDC. This is the value of VDC. And what else he asked? He asked us to find out the output voltage, the DC output voltage across the load resistor, and also the RMS value of ripple voltage. So we already know that the RMS value of ripple voltage, VR RMS, is given by IDC divided by 4 root 3 FC. IDC divided by 4 root 3 FC, where IDC is known, that is 50 into 10 to the power of minus 3 divided by 4 into root 3 is 0.732 into frequency is 50 into capacitance is 100 into 10 to the power of minus 6. So if you calculate this one, VR RMS value can be obtained as 1.4433 volts. This is nothing but the RMS value of ripple voltage across the capacitor. Okay, so now uh, RMS value of ripple voltage, and he has also asked us to find the ripple factor. So we already know that the ripple factor formula is given by VR RMS divided by VDC. So VR RMS value we have just found, that is the 1.4433 divided by VDC value we just found, that is 167.2056. So now if you calculate this one, we'll get the ripple factor gamma as 8.63 into 10 to the power of minus 3. So 10 to the power of minus 3 means 0.00863, which is very less. So what is the purpose of using a capacitive filter? In order to reduce the AC components present in the output of the rectifier. If you reduce the AC components, obviously the ripple factor will be reduced. So that means basically the ripple factor of full wave rectifier is 1.11. So now after using the capacitive filter, it got reduced. So that is the importance of capacitive filter. So that is the second problem. Now the next one, for a full wave rectifier circuit, the secondary transformer voltage is 30 volts. It is in the RMS value with a frequency of 50 Hz. If the ripple voltage in the output should not exceed 2 volts peak to peak. If the ripple voltage in the output should not exceed 2 volts peak to peak with RL 250 ohms, calculate the necessary capacitor required. So he gave us the ripple voltage peak to peak. It should not exceed that, and such that the resistance, low resistance is given, and he asked us to find out, in order to have a ripple voltage not greater than 2 volts peak to peak, what must be the capacitor that we need to use? That is the question. So first let us list all the parameters that are given here. So first of all, Vs RMS is given, so which is given by 30 volts. So it is mentioned that secondary transformer voltage is 30 volts, that is RMS value. That is secondary RMS value is given by 30 volts. And he has mentioned that F is equals to 50 Hertz and RL is given, that is 250 ohms. Okay. And he has mentioned that VR peak to peak, that is a ripple voltage peak to peak is 2 volts. Now he asked us to find out the new the capacitor value such that the ripple voltage peak to peak must not exceed this one. So in order to find out the capacitor value, first we have to find the gamma, that is a ripple. First of all, we should have formula here. We have the formula, that is VR. Just a second. We have the formula VR peak to peak is given by VDC by 2FC into RL. VDC by 2FC into RL. So we can also write this one as IDC divided by 2 into FC. We can also write like this. Okay. So that is VR peak to peak is given by IDC divided by 2FC. So here we know that the VR peak to peak, that is 2 volts, is equals to IDC we don't know. IDC 2 into F is 50 into C. So from this I can calculate the value of IDC by C as 2 into 50. So that is 4 into 50 is 200. What is this? This is the value of IDC by C. So IDC by C value is known. So IDC by C we have calculated, which is equals to 200. Which is equals to 200. So we already know that VDC is equals to VSM minus IDC divided by 4FC. IDC divided by 4FC. So where VSM is nothing but, how can I calculate VSM? As I know the RMS value, root 2 into RMS, VS RMS. So root 2 into 30 minus IDC by C is known, that is 200 divided by 4 into F. 4 into F is 50. So this is VDC value. So if you calculate this VDC value, we'll be getting this value as 41.4264 volts. This is the value of VDC. Okay. So now, what I have to do, I want to calculate the ripple voltage. I want to calculate the capacitor value such that the ripple voltage should not exceed the 2 volts peak to peak. So that is, we already have the ripple voltage formula, that is VDC by 2FC into RL in case of full wave rectifier. So now here, now substitute the value ripple voltage, that is 2 into VDC value. Just now we have calculated. What is that? That is 41.4264. 41.4264 divided by 2 into F is 50. C I have to calculate, and RL value, we know that RL value is given, that is 250. So now by we can calculate from this. I can calculate the value of capacitance as 41.4264 divided by 2 into 50 into 250. If I calculate this value, then I will get the capacitance value as 828.528 microfarad. So this is the value of capacitance that is required in order to maintain the ripple voltage not more than 2 volts peak to peak. So this is how we can solve the problem. Next, fourth one, what is the ripple factor if a power supply of 220 volts 50 hertz is to be full wave rectifier and filtered with a 220 microfarad capacitor before delivering to a resistive load? That means before delivering to the resistive load, it should be filtered by a capacitor of 220 microfarad and the resistive load resistance is also given, that is 120 ohm. Compute the value of capacitor for the ripple factor to be less than 15%. That means he asked us to find the capacitance value required for a new ripple factor which must be less than 15% of the ripple factor for the above specification given. So first of all, let us note down what are all the values given here. So here 220 volts given, that means it indicates VP RMS, that is 220 volts. That is the primary, the RMS value of voltage at the primary winding, which is, and the frequency is given 50 hertz, and the capacitance is given, that is 220 microfarad, and the load resistance is given, that is 120 ohms. Now, first of all, we have to calculate the ripple factor. So we already know the ripple factor formula for a full wave rectifier with capacitive filter, 1 by 4 root 3 FC into RL. 1 by 4 root 3 FC into RL. Just we know all these values, just substitute all of this. 1 by 4 into 0.732 into F is 50 into C is 220 into 10 to the power of minus 6 into RL value is 120. So if you calculate the denominator, we will be getting it as 3.8649. So this is the, if you calculate this one, we will be getting it as 0.258. So that means for the given capacitance value, the ripple factor is 0.258. Now, he asked us to find the capacitor value which is to be used in order to get a ripple factor which is less than 15%, which is 15% less than this one. So that means we are finding ripple factor, new ripple factor. So that is 15%, that is 0.25 new ripple factor 8 minus 15% of 0.258 into 0.15. So 15% means 0.15. We are finding the new ripple factor which is 15% less than this one. So ripple factor new which can be obtained as 0.22. So this is my new ripple factor. Now for this one, I want to calculate the capacitor value. As you know the formula, 1 by 4 root 3 FC into RL here. So I want to find out new capacitance value. So the new ripple factor is known 0.22 divided by 4 into 0.732 into F is 50 and C we have to calculate, C new we have to calculate, and RL we are not at all changing any other parameters, only the ripple factor we are changing. So now the C new can be obtained as 1 divided by 4 into 0.732 into 50 into 120 into 0.22. If I calculate this one, C new, the new capacitance value which is to be used is given by 3864.96, and if you calculate this value, you will be getting it as 258.7 microfarad. So, as we can observe that ripple factor and capacitance are inversely proportional. If capacitance reduce, ripple factor increases. If capacitance increase, ripple factor decrease. So here what we have done, we have reduced the ripple factor so that the capacitance got increased. Initially it was 220 microfarad. Now I have reduced my ripple factor by 15%. That is, my new ripple factor is 0.22 and hence the capacitance is increased. That means we have to use 258.7 microfarad capacitance in order to maintain a ripple factor which is 15% less than the previous one. Now coming to the fifth one, a full wave rectifier delivers 50 watts to a load of 200 ohms. If the ripple factor is 1%, calculate the AC ripple voltage across the load. So we already know that ripple factor formula is VRRMS divided by VDC, right? What he asked, he has given ripple factor that is 1%. What is that? 0.01. Okay. And he asked us to find out AC ripple voltage across the load. That means RMS value of ripple voltage across the load. That means we have to find out VRRMS. Okay. And he has given that PDC. What is this? Full wave rectifier delivers 50 watts to a load. Means this indicates the DC power delivered to the load which is given by 50 watts. And he has also given that RL which is 200 ohms. Now he asked us to find this VRRMS. In order to find out VRRMS, first of all, I should know gamma into VDC, where gamma is already given, and now I have to calculate VDC. So we already know that PDC is given by VDC square into RL, right? So from this, VDC can be calculated as PDC divided by RL into under root. So what is PDC here? PDC is 50 divided by RL is 200 under root. So this one get cancelled. So this will be VDC value will be 0.5. As you know the VDC value, now as I want to calculate the RMS value of ripple voltage across the load resistor, so that is equals to gamma into VDC, where gamma is given 0.01 into 0.5, which is nothing but 0.05 volts. So this is the VRRMS. So these are all the different kinds of problems that may be asked on the full wave rectifier. That means by giving different parameters, he will be asking us to find the various characteristic parameters of a full wave rectifier, like efficiency, ripple factor, or else the DC output voltage across the load, or else the peak to peak ripple voltage. So like that he can ask anything. In order to solve any kind of problem for the given specifications, so we should be familiar with the formula related to the full wave rectifier. So just be perfect with the formula so that you can solve any kind of problems. So I hope it is clear to everyone, and I hope you can solve any problems on the full wave rectifier. Thank you, one and all.
Like, share and subscribe. Hit the bell icon for more updates.